So yesterday I promised you that today I would like to make some proofs with you. And the proofs are first because proofs are nice itself, because they do not prove something, but they also give you some insights into the nature of the problem that you consider. We are talking about hybrid systems, so hybrid automata in this case, and this is very powerful. And we talked yesterday about the reachability problem, what it is and how we can solve it for the very, very basic subclass of timed automata, if you remember. So the reachability problem for timed automata is decidable, and we gave a constructive proof, basically, because we gave an algorithm based on abstraction. So since this algorithm can be proven sound and complete, we prove that the problem is decidable. So now today I would like to look at some further subsets. So this is what we know, okay? And then there are other classes of hybrid automata for which we can also pose the same question. Is there any algorithm that, given an automaton from that class, it can always decide whether a given state or set of state is reachable? And probably you also know what is the general technique if I want to prove decidability or undecidability. What do you do? So during your studies, probably you have been confronted with decidability or undecidability.
Reduce it to another undecidable problem.
Reduce all in mass, right? You want to solve something, it is not known how to do it. If you can give a reduction to another class of problems, then you are done, right? You did not need to do much, you just need to show equivalence of the hardness of the problem, okay? And depending on what I want to prove, I lead back different things to different classes. So if I want to prove decidability of a class of problems, what do I need to do? So I have a problem, let's call it A. I want to show decidability. So this is a set of problems. I want to know whether there exists an algorithm that I give him any of these problems and it gives me the answer. And I know that this is decidable. I have an algorithm for doing so, or I can lead it back to something else. What do I need to do? I do not want to prove this constructively. I do not want to give an algorithm. What do I do? What do you mean with abstraction? Abstraction is a certain kind of this. I need an algorithm. This abstraction means I need an algorithm that takes any problem from here and transforms it to a problem here. And what kind of property does this transformation need to have? I mean, at the end, I want also to know the result. I want something that takes any problem from here and tells me the result.
It has to be reversible.
Exactly. So I transform these problems to these problems. This is a transformation. This I can solve, right? I have a result for B. And from that, I need to be able to construct the result from A. So this transformation is not just any. I must not lose information by doing so. OK? And then, if it is correct, then I get the same as if I would have solved this problem. So if I want to prove that this is decidable, I do it this way. If I additionally want to prove that it is the same hardness, right? This is not harder than that. Then the complexity of this transformation also plays a role. So if I want to show, for example, if this has exponential complexity, that means I need exponential effort to solve it, and this is polynomial, then I could take an exponential effort in transforming, then I basically solve the problem. Okay? So if I want to show that the same complexity, then this complexity must be less than the complexity of the class. But now it is only doability. Okay? So let us say it doesn't matter, but the transformations we consider will be polynomial. Now it is for decidability. What if I want to show undecidability? okay, it's not so easy to. Undecidability of A. And I know that B is undecidable. What do I have to do then? So I know B, there's no algorithm solving all instances of B. And I want to show that A is undecidable. What do I do? It is similar, but
maybe show that you can transform B into A.
Exactly. I show that if I give a transformation that transforms each B problem to an A problem, and now I know that B is undecidable. So if I could solve A, then I would have solved B. So once I can do this transformation, I have proven undecidability. Okay? Because I know that this one does not exist. I cannot solve all B instances with a single algorithm. So if I can transform all B problem to an A problem, such that if I would have the result here, then I would have the result there, then I know no way A is undecidable. Okay? So let us now look for both of these two types of problems. Let us look at some examples. And the first one, what I would like to show you, is timed automata. It's just the very simple case where all derivatives are 1. That means I have only clocks. Okay, so timed automaton has just clocks and only clocks compared to constants and clocks reset to 0. Very, very simple. So we can show that we can relax this one to reset to constant, but not much more is possible without losing decidability. But a bit is possible. A bit is possible if we take rectangular automata, then we relax 1 and 0 to constants. Actually, we can keep this one, it doesn't matter. But I say that these are all from intervals, where C1 and C2 are rational numbers, so do not involve any variables. And then I can say that X is from some interval, and I can reset X to some interval. Where this from an interval to an interval means non-deterministic choice, so any. I do not exactly know what, but any. So this class is already undecidable. But if I put an additional condition on it, it becomes decidable. And this additional condition is that it is initialized. That means now the derivative can be different in one location. So if the derivative is one interval, and then the control location is changed where the derivative is from another interval, a different one. So if the derivative changes, so they are not, the behavior changes, the dynamics changes, then I have to reset X. Intuitively, it means that if I have some behavior and change this behavior, I cannot just take arbitrary linear combinations. This is not possible. The only thing what I can do is, once I'm here, I change the behavior, but I know where I continue afterwards. No, not exactly, but an interval. I know where I will continue. Okay? And then if I reset again, I know where I can continue. So this linear combination is quite restricted. And this allows us to analyze the behavior in a piecewise manner. Okay? So it seems not so strong, this restriction initialized at the first site. If the dynamic changes, I have to reset. But in expressiveness, it is a high price. But it saves us in the sense that the problem is decidable. So, and then you can prove it, this is here, by leading back to a known problem, namely timed automata. And it is in several steps, and I don't have time to show you all the steps, but I chosen the first one here, from initialized stopwatch to timed automata, just to give you an idea how it works. So this is rectangular automata, I already told you, but I did not tell you what rectangles it's, but that you can imagine these are boxes. So Cartesian product of intervals. That means in your automata, all conditions are now rectangles. So the derivatives are from boxes, the clock values are from boxes, the invariants tell you rectangular conditions, and you reset to rectangles. And then here I have an example. So the derivatives are from boxes now, whereas boxes says that the different dimensions are independent, right? I cannot put x dot to y. Only x dot to a certain interval and y dot to a certain interval independently. And here an example, you can also reset values to some values from interval chosen non-deterministically. Okay. Initialized, I explained you what it means. And this is the transformation, and I show you the first one. So timed automata here, derivative 1 compared to constants, reset to 0. And now initialized stopwatch automata is a bit stronger. Stopwatch means we have derivatives stopwatch automata. The derivative is, I write here, either 0 or 1. That's it. So it is only a bit stronger than timed automata. You can stop your watches. But if it is not initialized, already undecidable. So you see, this is, you get very, very easily to undecidable problems where there is no algorithm solving them in general. Okay, but if it is initialized, that means when I change the derivative, means then I stop, for example, my watch. Here it was running. Here it does not run anymore. Then I have to set the value. For example, I set it to 2. Okay? Then it is decidable. If I don't do this, undecidable. Let us check how we prove it, and I prove it by letting it back to timed automata. And I have an example here, so I do not show it in its full generation. This is just the definition of stopwatch automaton, this simple thing, a bit formally. And here's an example. So you have here a watch, this is running, and then you can stop it 2 ways. Either you move here, and then you come here, it is still stopped, or you stop it directly here, but it is initialized, so if you stop it, you set a value. Here you set it to 1, here you set it to 2, but you see here, on this transition, the derivative does not change, so I do not have to set it. Okay? And I want to know something here, whether something is reachable, so it might continue here. For example, if x is 3, then I can get here. Okay? So basically, I want to analyze reachability, and I define a general transformation of such automata to timed automata. So can we, the question, can we define now a timed automaton such that if I know which states are reachable in the timed automaton, then I know which states are reachable here? Think a moment. Now, if you should define this transformation. So here I can stop the watches. Now I need a model where I cannot stop watches. They are always running. But I can still mimic, simulate the behavior of this one. I can tell if the transformed timed automaton, I know the reachable set. I can tell you the reachable set there. What do you think? What is the key issue? Just take a minute to think. So obviously, the first location, L0, is not a problem because the watch is running there, right? And now I assume we get here in L2, but I cannot stop the watch. So it must run there. No way of stopping it in timed automata. So what is the value of x here? It is running. So I come in, and and when I enter, I reset it to 1, but here it is running. So in the timed automaton, yes?
That one says x prime equals 0. L2.
Exactly, it is 0 there.
Yeah.
Because that is a stopwatch automaton.
Yeah.
But here, it's a timed automaton, I cannot stop it. Okay, now I try to find the transformation. I cannot write a 0 there.
Maybe a closed loop on L2 where you reset it to 1.
Why to 1?
Reset x to 1.
Because its value is 1 in the original model. I cannot stop it here, but I know. In the other model, its value is 1. Excellent. So let me write it here. Button means x is running. And if I write a number, it is the value. I know that in the original system, this is the value. So if I want to transform, I know reachability in this model. Here, I take the reachable states. And for this location, I replace the value of x by 1. That is the reachable state, OK? Actually, nearly that's it. But let us go to the other one. So what do I do here? So the value of x, now when I enter it here, it's 2. But I have also this one. So now what is the value of x there in location L1?
The value of x.
What is the value of x here? So I can enter it from 2 ways. And actually, the value of the derivative of x is 0. But I cannot stop the watch. So I must write here a 1. That means if I analyze reachability here, then I will get some values for x. But now I want to generate the reachable set, the values reachable in L1 for x. But here, I cannot stop it. So what to do?
Can't you just add a new state?
Exactly, add a new state. Because I can reach it from 2 different ways. I make 2 copies. First, I remove this one. I just, for each state, each location where x dot is 0, so the watch is stopped, I check how many different ways was x set. X was set to 1 and to 2. So entering L1, I have 2 different possibilities where I stopped the watch was either at value 1 or at value 2. So I make 2 copies. Here for value 1, L1. And here for the value 2. And now I check. For each transition, from L0 to L1, it is stopping the watch. Then I go to the copy because the automaton is initialized. I know when I stop it, I reset it. So I know to which copy I should go. From L0 to L1, where x is 2. So now I add this transition. Actually, I reset it, but it doesn't matter, because in this location, 2, the other way around. I reset it, but it doesn't matter, because here I replace all x values just by 2, once I know the reachability. For the other way, when I stop the watch from L0 to L1, then I stop it by setting it to 1. And then from L2 to L1, it remains stopped. So I will go from the same copy to the same copy. So if I go from L1, what did I do from L? Yes, I just would have been better the other way around, but from L0, I stop by 2. From L0, I stop by the value 1. And now from here, from L2, I can get to L1, but I keep the values. So here I can go. Okay? Now I compute reachability here. For example, if there is a transition going out with if x equals 3, then I can continue. Then note that here, with x equals 3, I could go, because I start by 2 and it increases. So I need a bit additional, because there I cannot go transition x equals 3 from L1, because it is always 2. So what I need to do, I have to replace each condition with the value. So I have 2 equals 3. Okay, so a bit more, but this is the basic idea. Okay, so this is one transformation showing decidability. I have another example which I just show you.
How do you reverse that transition?
You compute your reachability, which you know how to do, and that means you get for each location the set of reachable values. And there you replace the x value just by the constant with which the location is annotated.
Okay. Yeah.
Okay, and this is how it looks like. Good. Now I told you timed automata, you just can compare constants, clocks to constants. Oh, sorry. Clocks to constants. So what about adding something more? Difference constraints. And I can also compare the difference of 2 clocks to constants. And this is possible. This you can still do without losing decidability. Not if you add also some. X plus y compares to c. That is already the two together lead to undecidability. So let us now check difference constraints. So in my system, I have now also this, where in timed automata, I can only compare x to constant or y to constant, but not their difference. So if you want to show that this is decidable, we don't have so much time to show. I show you the basic idea is now as we added copies for the values where what is stopped in the previous example, now we add 2 copies, one copy where this holds and one copy where this does not hold, for each difference constraint in our model. So here I have a copy where it holds, here I have a copy where it does not hold. And then I adapt each possible transition. So if I start with both being 0, I analyze 0 minus 0 is 0 less or equals c, a constant, and assume it is non-negative integer. It's not a restriction, we can extend it, but if it is non-negative, then that means this holds always, so I can only start in this copy. What happens if I, on a transition, reset x to 0? Well, assume I am in this copy, I reset x to 0. So previously, x minus y was less or equal a constant, and x is non-negative, it's a clock. So if I reset x to 0, then this difference gets smaller. If it was less or equal c before, it is also less or equal c after, so I remain in this copy. In contrast, if x minus y was larger than c before, and I reset x to 0, that means y is a clock, it is non-negative. Minus y means it is not positive, so it is less or equal 0, but it should be larger than a non-negative constant. It cannot be. Okay? So I always move by resetting x to 0 from this copy to here. I can do something similar for resetting y. It is actually mirrored. Interesting is now for those transitions, if I'm in this copy, I just execute them without any condition remaining in this copy. Because if it was true before, I do not reset, it will be true after. And I cannot do such transitions in these copies. So this way, I could express those conditions in the formalisms of timed automata. Okay? I have again a transformation from models with different constraints to models without different constraints by doubling the location space. Okay. Now, let us go one step further where we get to undecidability to show you also an undecidability proof. So, a skewed clock is this we already know from rectangular automata. So the derivative is a constant. Means it runs at constant rate in all locations the same rate. Okay, like for a watch, it is always the derivative is 1. Now, for example, I have a clock that runs double as fast, then the derivative is 2 in all locations. It does not change. Okay? It runs always on the same speed, but it is not necessarily 1. This is a skewed clock. And the multi-rate time system is a system where you have at least 2 different rates of clocks. So you have skewed clocks with different speeds. And the same as clocks, we can reset them to 0 and compare them to constants. Then they are decidable. Okay? But if I have now also these difference constraints or equality constraints x minus y equals to 0 already suffices, then it gets undecidable. Because as long as I do not relate the dimensions to each other, I can skew each dimension, the speed of the clocks, I can slow down to 1, and the conditions that are to be reached are when the skewed clock reaches a value, I can also scale down with the same constant as I slow down the clock, such that they will be reached at the same time. But if I compare dimensions, then it is not possible anymore. Okay. So now for the undecidability proof, for this, if I have simple multi-rate timed systems, then it is decidable. And there's a very, very easy proof that it is decidable, because we already know that stopwatch automata are decidable if they are initialized. Okay? Now we have multi-rate time systems, but we can just, they are initialized, okay, because the derivative does not change. So we can just scale down just the basic idea. If you have, for example, x dot equals 2, and then have a condition if x is less or equal to 4, what do? You slow down the clock to 1, and you scale down also the condition, so with the same factor. Okay? But note, if I have another one, y dot equals 3, and I have y less than or equal 9, and I can, of course, also scale down y. But I scale them with different constants. So now if I would have a constant like x minus y is equals 0, then I would need to tell something like the half of x minus the third of y. Afterwards, 3 times. 2 times x. Exactly. 2x minus 3y equals 0. And this is not in the syntax. So I cannot do the same if I have these difference constraints. They really do matter. So as long as I do not compare dimensions, it's fine. If I compare dimensions, I lose decidability. Okay, this is just a proof that this transformation does not work, but it does not work in general. So if I want to prove it, for the simple case, without these constraints, this is what I told you. So I can scale down the derivatives to 1 and also scale down the conditions to 1. One problem appears that I allow only integers. So there is also a multiplication involved with the smallest common multiple of the derivatives is multiplied that we get integer value. It is not so important. The main idea is here. Okay, so one undecidability proof.
Can I have one?
Yes, sure.
So what you say that with the initialized stopwatch, so is the initialized to one value or to a set value?
It means that if the derivative changes, you have to set the value
Set
on the
just-
jump.
Okay, can
Any.
be non-deterministic. This
Any.
set. Yeah, okay.
But from a set. From a given set, you can choose non-deterministically. It can be shown that it doesn't matter whether you set it to a value or to an interval. Okay. And then, of course, if I make this transformation, if I know reachability here, I can compute reachability here. There is the function if you want to look it up later. So, undecidability proof. Now for undecidability, which problem do you know to be undecidable? Every computer science knows at least one such problem. Which is that?
The traveling salesman problem.
That is very complex, but that is still decidable. But if you start your studies, then you learn about termination of programs, right? The halting problem, right? The halting problem tells you that there is no algorithm such that you can give any Turing machine with an input and it gives you back the answer whether it terminates or not. You don't know this? Did you know? Okay, I don't have enough time. I would show you this proof. This is so elegant. This is genius. But I stay here because I don't have time to explain also the halting problem proof. So we assume that we know that it is undecidable. And basically what you do is deciding reachability for a very simple machine. So all the programs that you can generate is a kind of, you can think of assembler programs. So you have only a set of registers. We need only two. So you have two registers. They contain unsigned integers. And a program counter. So we have a sequence of statements that we want to execute. And these statements can be only increment one of the registers by 1, decrement one of the registers by 1 and let the other unchanged, or you compare the content of a register to 0. If it is true, you jump somewhere, otherwise you jump somewhere else in your program. That's all. No classes, no objects, no pointers. And here it is already undecidable where you get whether these programs terminate or not. Okay. So now if we want something to be undecidable, and now I will prove that multi-rate systems, if they are not simple, they are already undecidable. So multi-rate means we will have two different rates of clocks, skewed clocks. So two clocks, they run always with the same speed, but at different speeds. And if I can compare them, I have these different constraints. So I have one clock running on one speed. Let me call this x1. And x2, the second clock, runs at a different speed. And I can check whether they are equal. That's already, so this is multi-rate, and simple if you don't have this, you cannot compare. Not simple if you can compare. And I show that these are undecidable by transforming such a program, two-counter machine, to this. So what we do need to transfer, so set up, changing the program count is easy because we can set a value. If I add something with derivative 0, then I just reset its value always to something. So these are easy. So, but already we have some problems with letting a variable unchanged. So I need to implement to let a register value unchanged, to increment one and to decrement one. That's all I have to. These are the challenging parts. But you see, if I have here something, assume this is 1, this is 2. So not 0. If they are 0, it is not so funny because I cannot do anything with it. And it is initialized, so I can reset them only to 0. But then, OK. So skewed clocks are always running, OK? Skewed clock is always running, time passes by. So time passes by means this is the time, and this is the value of a register. And I will encode such that at certain time points, the computations are, so if this is the ith computation step in my counter machine, then it is represented at a certain time point in my multi-rate timed system. And then the two counter machine does a computation step, and this is represented at another time point. So what I want, let the register unchanged, means I start here with a certain value, and I want to have the same value here. But where's the problem? You see, I cannot stop the watch. Its derivative is always constant. It's always the same. It is a clock, and it is not a stopwatch. I cannot stop it. So now we need an elegant idea to model that the value is unchanged. This is actually a funny problem because in discrete systems, you can change everything as you want to set them discretely. And now we have continuous. It is even more powerful, but we cannot stop it, cannot stop time. We cannot, everything evolves dynamically. So you have the feeling this is more powerful, but now we have the problem to prove it. To prove that we can simulate with dynamics also discrete behavior. So how to do it? I show you. Sorry, this I have to mention. So we have these two clocks, x1 and x2, with rate 1. Here we will encode the register values. And if the register value is n, then the value of this clock will be 1 divided to 2 to the n. This is because we cannot implement addition, but we can implement multiplication, halving and doubling. And we will take another clock y. This is a normal clock with rate 1. And if this is here time point ti, then ti plus 1 will be time point ti plus 2. That means one computation step of the two counter machine will be simulated by 2 time units. And I take this y to measure these 2 time units. And we will need some skewed clock. So up until now, everything has rate 1, so it's a timed automaton. We use another clock set of rate 1, and here set prime is a clock of rate 2. This makes the problem undecidable. So let us come back to unchanged register. The trick is easy. So now we start here with some value. If the register has the value n, then this clock xi or xj has the value 1 divided by 2 to the n. I start with it here, and after 2 time units, I want to reach the same value. And this is actually easy because what I do, I know n is a positive integer. That means 1 divided by 2n is between 0 and 1. Okay? I let the clock run, and when it reaches the value 1, I reset it to 0 and let it run. So you can see that after 1 time unit, I reach the same value. Because this time here, until I reach 1, is 1 minus this value. So the remaining time for 1 is the original value. And I do it twice. And after 2 time units, I have the same value. Nice. And this can be encoded by an automaton here. OK. Now incrementing a register is a bit more complicated, and we need non-determinism. But it can be done. So what we do is, again, so I want xj. It is a register. It starts by 1 divided by 2n, and n is incremented. So after 2 time units, I want to have this value, 1 divided by 2 to the n plus 1. That is, I simulate the register value from n to n plus 1. OK. Now what I do is I let it again run to 1. So I know that the remaining time here till the end of the time unit is the original value. And somehow I need to halve it. Okay, but I cannot use divided by 2 in my model. So what I first use is to guess. At this time point, when it reaches the value 1, I reset my clock z, which runs at speed 1. I reset it to 0 and let it run. And before this time unit ends, I reset my auxiliary clock that runs double fast, non-deterministically, at within this time interval. I reset it to 0 and let it run. So now if after the end of the time unit, their value is equal, then I guessed right. And I guessed here just the half of this time interval. OK? And if I guessed it right, it means that this time interval here is the half. So if I reset also my register at the same time with the skewed clock to 0, then it has now half of the value. OK, once more. When the clock, the register reaches the value 1, I reset my auxiliary clock z to 0 and let it run till the end of the time unit. That means its value will be 1 divided by 2 to the n. Non-deterministically, I reset my auxiliary clock with double speed to 0 and also my register to 0. So now it runs at double speed. So if after the 1 time unit, the 2 auxiliary clocks have the same value, then this was guessed right to be the middle. And that means that then my reset register has the required value. So I said guessed non-deterministically. And if I am right, then it has the right value. How to make use of it? Well, I define an automaton, which here is the condition. I'm here at this time point. Then I can check if y has the value 1, so y measures the time, that means this time point has been reached, and z equals z prime, only then I continue. That means if I guessed wrongly, I have a deadlock. But if I analyze reachability in this automaton, I will reach here only if this condition was right. That means if I guessed right. So once I analyze reachability here, and I know I reach this point, then I know my register value will be increased by 1. Okay, so this is the way how non-deterministic automata is more powerful, because you do not need division by 2, you just guess, and if you can check whether you guessed right, then it is okay. You just introduce some unuseful stuff, namely wrong guesses, But if the right guess is under it, and you can check whether your guess was right, then it is still sufficient. And we can check because we can compare skewed clocks values to each other. If we cannot, it's decidable. Then we cannot simulate the two register machines. Okay. And the last, decrementing, it is a bit more complicated. I don't have time to explain, but it's similar. It is just that previously we resetted the register with the faster clock, but now we want to, by decrementing, we want to go from a smaller value to a larger value. So basically, this will be the right value. If I incremented, then the smaller value was the right. Now I decrement, so the larger value is the right. But I cannot reset the register with the same time because it is before that reaches. So I must guess the right point before my register reaches the value 1. So I cannot reset that. But actually, this is, if I guess right, then this clock has the right value. And that's why we need 2 time units, because now I have to copy this value to the register. Means I let this run till it reaches 1, and then I reset my register variable, and I get after 2 time units the right value in it. So it is a bit more complicated, but it is still possible. You see that this way you can model discrete computations, but it is not trivial how to do it. But it is also interesting because it shows you which small syntactical differences make which effects in decidability, but in complexity it is similar. There you have also similar proofs. Okay, so now I am done with the proof part, and tomorrow I will tell you something about over-approximative methods. So we have a tool Hypro and a tool Flowstar. What ideas are beyond that to use flow pipe construction to over-approximate reachability of more powerful hybrid automata? Thank you.
Thank you very much, Erika. Any questions? Questions from the audience?
Yes, I have a question. So, for example, how do you compare with the O minimality approach for the decidability?
So the initialized rectangular automata is an instance of an O minimal.
Yes, so but I mean that here is that like we can see that we reduce to something that we know, but then about the O minimality, it's a different concept. So it's a
I do not exactly know O minimality, but what you can see is O minimality is something like that, and the initialized rectangular automata is on this surface. So O minimality is more general.
Yes.
And then you can instantiate it to this instance. But O minimality would allow you to generate more instances at this surface between, so which is still decidable, but if you go a bit further, it gets undecidable. So this is really that describes the boundary between decidability and undecidability. But I did not go deep into it, so I cannot tell more. I have sabbatical in winter semester, perhaps I will have time.
No, because I'm thinking that, for example, the proof, the decidability of the linear dynamical systems, like with the eigenvalues and then change with the quantifier eliminations. So I know that, okay, there is an approach that I will try to reduce to some well-known example system in computer science, but also like in computer algebra. So there is, so that means that perhaps if we can have some kind of like a more universal approach of the reduction, or maybe beyond reduction or something that.
Yeah, so what I talked is decidability of the reachability problem. If you relax it, you can talk about decidability of the bounded reachability problem, which is kind of easier. So then you can express, increase expressivity and still be decidable for that bounded problem. That means you do not consider arbitrary lengths, runs, but only which have a bounded number of jumps,
Mhm.
so discrete steps. Then that problem is decidable for a longer case, and what Todd talks about is that how far you can go then to decide
To push
reachability.
the boundary.
Exactly. So then you can allow more things like, arbitrary derivatives. Then you can compare clocks. You can have linear combination. Let me call that linear combination of the variables, and you can set that to linear combinations, or also linear conditions as conditions. So everything, as long as everything is linear, it is not a problem. And then where it starts complicated, if you have also linear derivatives, then if this is nice, that means, for example, x dot equals 2x plus y. If this is nice, then you can still decide bounded reachability. So basically, they can compute the matrix exponential precisely. I will talk about it tomorrow. But then you can have, again, some disturbance. So this is the variables. This means either control or disturbance. Then it gets a bit more complicated, but if this is also nice, it is also not a problem. And then if you have really nasty systems, then you have x dot equals a function of the variables plus the function of control variables, which might be also trigonometric functions and so on. So then we talk about nonlinear systems, meaning that the derivatives are nonlinear, and then it gets really nasty and complicated. You lose all kind of decidability there. Even one step, what you can reach in t time. So it is not proven. So for example, by the exponential function, it is so longly lasting known, okay? So in mass it is so deep, the exponential function. And it is known, so not so long, it is 50 years, 60 years known that real algebra is decidable. But you learn at school, you have polynomial constraint systems, polynomials compared to zero, to decide whether it has a solution. It is already not trivial, but it was shown by Tarski first, that it is decidable. But now if you add the exponential function, no one knows till today. Not proven. It is assumed that it is undecidable. Depends on some conjuncture whether it's true or not. Fascinating. So whether you add exponential function here, not known what happens. So thank you. I wish you a nice lunch.